So we're doing this liquid tank, the two-tank liquid system, and we've talked about training the model, because that's actually what this thing uses as a neural net model. We talked about the two different ways to encode the inputs, either as their values or spread encoded as a pattern. So that was a feature. We finished talking about save best in NeuralWorks, where it trains and tests, and then picks the network with the best testing. Which you can do by hand, by the way, obviously. You try different network architectures. You can train, look at the RMS, and you can test, and look at the RMS, and then go train some more. All right, in the paper, they talk about two different ways to use the model. So they're validating. And they talk about two different ways to use the model. So they call it a system model. It's really what I would call a standalone system model. So you have the system itself. And it takes current control signal and it gives the actual height, because the system just runs as a system. And then our neural net model takes takes current and past sample of that, and then current and past sample of the input signal. And so these are the same thing here. And then the neural net model is going to put out an estimate called hat of the next height. So it takes the current height, past height, current and past valve settings, and it's going to predict the height at the next level. I'm going to erase up here because I need some room. And so to validate, you compare these two. But the two different methods of using the model have to do with where do you get these past signals. In other words, do you get the past signals from the actual system? Are you measuring it on the system and the system is running in parallel? Or do you run the neural net all by itself? In other words, the standalone method would be you bring this back, you run it through a time delay, and then run that through another time delay to get these passed. Like that, and you can actually run your model without even having the system there. So you start it out at initial conditions, you run one time step, and you use those values back here and feed them back in. Then get one more time step. You don't have to have the system there at all. With this method, the error can accumulate. And that was the reason that they came up with that spread encoding method, because I'll show you the spread encoding method gives better error. And they want to run the model without the system, because the way they develop their controller, it's not a neural net controller, is that they try a control signal, and then they run the model ahead a whole bunch of steps to see how well it does without running the system. And then they choose their control signals based on all of these simulations into the future. Then they run it one time step with the actual system. Then they do the whole thing again. So they're using the model as predicting the future, essentially, of how the system would run with different input signals. And then it allows them to optimize the input signals and then use it in the actual system. So this thing has to run a whole bunch of times for each real-time time step that's going on with the system. So they wanted their model to be super accurate because they want to run forward without the system running there. And then the other way they can use it is what they call a one-step ahead predictor. And this would be assuming that you are running the system synchronously with your model. Every time step that the model goes forward one time step, the system actually runs ahead one time step and you measure off the system. And so what changes there is where this feedback signal comes from. Instead of coming from the model, since you're running the system, you get it from the actual system. So you have a sensor on board the system. And essentially that resets the data to what the system is actually doing. And so you can see the error would not accumulate then. So I'm going to show you some figures in the paper. Figure 6.5 is the single node data model, one step ahead. And then figure 6.6 is the spread encoding, one step ahead. And the idea here is they're going to show the spread encoding is better than the single node data model, but especially when they're doing the standalone method. So figure 6.7, so the single node data model is as a model. If you want to write standalone, because if I were writing this paper, I would have called this standalone because it's standing all alone by itself. And then they compare the single node data model to the spread encoding. And then I'm going to list all the figures I'm going to show you here just so you can look at them later. Then they say, okay, they're going to put in random inputs, because these are step inputs. And this is spread encoding, and this is single node data model is figure 6.10. Let's see, I like this one. Isn't it weird how every time you cough, you think, wow, are people looking at me and thinking I'm sick? Are you guys eligible for vaccines? No?
Yeah, you do not a student. No. Like on
You're
your
the
WSU.
student,
Yeah. On your WSU, there should be something.
Yeah, there was some debate. Initially, it looked like it was just employees of the university. But then when I looked at it, it looked like students could sign up whether you were working for the university or not, which I think is great. Why not? I need to show you this on the screen. So this is 6.5 single node data model. And this is one step ahead. And then 6.6, I need to scroll down. This is another one that I showed you over here. That's where they did the spread encoding. I figured that. Let's see if I can do it. That it keeps wanting to scroll down to the bottom. I'm not sure why. Try again. And this one's causing problems. Let's try to do it. There we go. Just because it's Monday and the time changed. Huh? Okay. So the single node data model, one step ahead, is the top one, and then the spread encoding network. I'm not sharing my screen now. Obviously, I'm affected by the time change. I'll share that. All right, now we're cooking. So the spread encoding versus the single node data model are the two plots on the left. And this is the one step ahead where the error does not accumulate, and it's hard to tell that one's better than the other, right? Because it really, the error only increases with one step, and then it gets corrected back to the model. But they're showing here why they need much more accurate results if they want to run this ahead all by itself without the system. So look on the right, the top is single node data model. You see some error building up. So that means it's going to throw off their controller if they rely on this to propagate forward to see how well it does. And here's the spread encoding network down here, a lot better error. Again, as I said last time, I don't know for sure that if they couldn't have gotten just as good a results without spread encoding, but they put more hidden neurons in there, but they didn't do that study. And as you employ neural nets in your work, it's pretty much trying different things and seeing how well it works and finding the best solution. The good news is there's more than one solution. There's a whole bunch out there, and so you can usually find a good solution. And then there's a comparison between random inputs for the spread encoding and the single node data model. Sorry, this is spread encoding, so they settled on that. So essentially, they validated the model. It gives good results, and they can use it in their controller. Now, the controller itself, as I mentioned, the reason I'm showing you this is not because it's a neural net controller, but because it shows a way to use a model to train a model. So two different methods to train a model and use it. And then the other reason is we got the spread encoding. So I was showing you for that reason. And then the save best that I wanted to demonstrate. So they talk about that. So as far as the controller goes, you can look at the paper, but what they're showing is the neural net model is used to predict the future on how the system behaves. And then they have a completely classical, no artificial intelligence optimization process to pick the control signals. So that's all you really need to write down, the controller. Not a neural net. Neural net model is used to try out various control signals u as a function of time. I'm drawing a line. Does various have, it didn't have an E on the end of it. Well, you guys are engineers, you know how to spell, right? Correct? Sure. All right, so again, there is no neural net control architecture in this paper. So I'll show you the results, and then we're going to ask the 3 questions. So here's 2 different sets of results. They're trying to track this step signal here, the dotted line. And the actual system is the black line. And again, they're showing the results of the control signal that they developed using the model, but putting in the actual system. And it looks like it tracks pretty well. But then they show the valve. This is the opening and closing of the valve as this thing tries to control this real precisely. And you can see that there's a lot of valve activity. This is one of the things that if you ever take a class in optimal control, you'll learn that the controller effort, the effort of the actual system to track the reference sometimes is important. And like in this case, if you ran this for very long with that valve opening, closing, it's going to wear the valve out. So often you'll want to add another term in the controller design that minimizes the control effort, which is how much effort that valve has to do to track. And so what they did was they cranked it down. They said, we want to minimize both the tracking and the control effort. And they show over here that they can do a decent job of tracking the signal approximately with a lot less control effort. Again, that gets into stuff that's beyond the scope of this class, but I just wanted you to be aware that that's what they're showing in this paper when they talk about that. So the 3 questions. What's the application? These are the kind of questions that could be on the exam. What's the application? When we got lost in the details. What's the system? It's controlling columns. Yeah, the liquid levels in the 2 tanks, right? All right, so why is it a good neural net application?
Non-linear and you don't have inputs for the first column or first.
Yeah, so he's nailed it. There's, I mean, it's not like the distillation column where the system is just so many state variables that you can't. It's a pretty simple system, but it's non-linear. And they're trying to show that even if they don't measure one of the hidden variables, that they can still do the control manipulation. So let's see. So that's the system. That's the benefits of using a neural net. So that's the other question. And then the 3rd question is, what controller architecture was used? The answer to that was controller is not a neural net. It's just an optimal control process, but it used a model. So the neural net for this deal was to model the system, and that was it. Okay, so again, every time I show you an application, make sure that I answer those questions, those three basic questions. Yeah, that's it. So I'm not going to, the next topic that we're going to cover in this class is chapter 4. Let me make sure I'm sending you the right chapter. Yeah, chapter 4 in the book. But I'm not going to start that until we get down to the test, because it's kind of a completely different kind of neural net thing. So I want to do that. But I do want to just take a quick aside and show you how a network can operate if you have feedback connections in the network. We've done all feed-forward networks. I want to show you what happens if you have feedback connections, and at least that way you'll, if you ever see a paper about it, what's called a recurrent network, you'll go, oh yeah, I know where I can go look that up and figure it out. Let's see, let me just stop sharing this. Before I get into that, you guys finished your rotary arm problem, right? You're working on the 2-link robot arm. Probably haven't gotten much on that yet because of the exam coming up, right? Okay, just again, same advice on that one. Don't wait until the day before to work on it. If you get stuck, it's the day before. It's going to be Sunday, right? When is it due? Sorry, is it due on Monday or Wednesday? Tuesday? No. Wednesday, March 10th. No, that's the review.
Yeah.
Oh, gosh, I didn't change that. It is due on Tuesday. You guys better have it done on Tuesday. When is the 22nd?
Monday.
Is that a
22nd
Monday?
is Monday. Yeah, it's my birthday. So that's why I know it's
Okay,
Monday.
good for you. Happy birthday. So it's due next Monday, right?
Yeah.
Yeah, okay, that's what I intended. I just didn't change the Tuesday to a Monday. All right. So we'll bring in cupcakes on that Monday for your birthday. Any questions on that project? Anybody look at it and say, what the heck's going on? It's pretty straightforward. Just generate your data. You have to figure out your strategy for varying theta 1 and theta 2. And then you just flip the data, so that's easy. All right, so we've been talking about feed forward. Which the way we've drawn them is that the input comes into the bottom, or you can draw them in direction you want. But the main thing is there's only information flowing in one direction. From an input layer to a hidden layer to an output layer. And all of the connections go forward. That's what's called feed forward, because all the information feeds forward. Right? So that's feed forward. No recurrent or feedback connections. And this is great for representing functions and classification and things like that. Great for especially function approximation. Because that's what we do in here. We approximate either a model function, like we did with system modeling, right, where you have inputs mapped to outputs, and that's a function. That's why I wrote it as an F of a big bracket with all the data going in. Or the controller is a function. It takes the current state and the reference data, and it's a controller function that then gives the control signal. And so we write this as we've been doing this all along, is that we have a set of outputs that are some function of data going in. If it's a model, then these are the system inputs here. Double brackets, not good. There we go. So the inputs that go into the system model or into the controller, and then these are the outputs that we need to do whatever we're trying to calculate. And there's a whole bunch of theory behind this. Your textbook has some of the information about that. This is pages 328 through 329. There's a bunch of high-powered mathematicians who apply theorems that have been around for a while about function approximation. And the theory says that if you have a smooth, let me spell smooth, smooth enough function. And the math guys don't say smooth enough. They actually define it in terms of math terms, but it's a piecewise continuous function, so there's different classes of functions. But they say if your function is not really super discontinuous, then a neural net can be found with enough hidden neurons that makes the error less than epsilon, where epsilon is a small number. This is typical of a lot of the mathematical, what are called existence theorems. Essentially what we're saying is if we have a function, does there exist a neural net that gives us 1% accuracy? Or 0.1% accuracy? And that's really all they're saying here is, you tell me how much accuracy I want. So let's say epsilon is 0.01%. So I want my RMS less than 0.01%. The theorem says that you can, it doesn't tell you how many hidden neurons you need, but it says that you can find enough hidden neurons that make your error less than that. It doesn't say how to find them. It just says that there exists a solution, which is important in a mathematical sense and in a practical sense as well, right? Because why go looking for a solution if you don't know that it actually exists? So this is an existence theorem. This was really important because it said that this type of neural net architecture can approximate a whole bunch of different kinds of functions. Remember way back to the perceptron, we found out that the perceptron with just one layer could not do the XOR. So what that meant was that with the perceptron architecture, it could not approximate those nonlinear XOR functions. And this theorem says, well, if you put a hidden layer in there and you put enough neurons, you can approximate a whole bunch of important and interesting mappings of the kind that we do in controls. So that's the story, the theory behind that, and that's all we're going to do. Now, a recurrent network does a completely different kind of thing. And when we go into this, keep in mind that the way this thing works is we set our inputs. Let's say we're doing the iris. You put the 4 measurements in, and you calculate your outputs, and you're done, right? One shot. Okay, so now let me draw a recurrent network. formulas we use over here are still the same, so let me write those up here. The output of each neuron is the activation function applied to the net input, right? And the signals coming in, you multiply by the weights, add it up, net input goes up here, but because of the structure, it all happens one shot through and you're done. The recurrent network uses the same thing, but it allows not just those forward connections, so we'll draw the forward connections in like this, but it also allows connections like the output of this neuron can go back into this one. Or the output of one of these can go back, well, that can go into this one, right? So those are feedback connections. You go, okay, big deal. We just draw them in and we do it, right? But let's say we're trying to calculate the X or the output of this neuron. To do that, I need to know, well, I know the weight here, but I need to know the X value here, right? But the X value here has to be calculated from output up here, and to get the output up here, I need the X value here, which needs the output. So it's this feedback connection. And so you can't process it in the same way that this thing is done, where you pop the inputs in, you calculate, you're done. So really, in order to start this whole thing off, is we need initial conditions. Initial values, initial conditions for all of the X values, all of the outputs. You start the network out in a certain state, and then you run forward. If you really do it, you run forward in time. If you want to think of each time step, each time you process the new X's, you use the same formulas, it's just now you start out and you have X's as initial conditions at time 0. You calculate all the U's, put them in here, and then you get X's at the new iteration. Then you use those new X's and then go back into the formula. And so the initial conditions start you off at a certain state. And so really, to write the equations for the propagation, we need to write it like this. Put it in terms of U and X's. So we have to calculate the U's first. So there's the net input for neuron I. And notice that any neuron is now allowed to have an input because we don't have the layer structure of propagation from input to output. Any neuron can have an external input. Because this neuron down here can take inputs from other neurons as well as that input. It's more complicated, but it's exactly the same thing. We just have to keep track of what all is going into each neuron. The processing is the same. You start with initial conditions. You send those into all the neurons, calculate the net inputs, multiply by the weights, and then you get new values coming out at the next time step, and that's what these equations are saying. You take current values of the system, multiply by the weights, add the input coming in, get the net, put the net in, get the F, get the new X, and then you do it all over again. And notice that now this thing is essentially a dynamical system. And it can solve optimization problems. All right. write this over here. Make it bigger. So the main reasons, the main uses that people have found for these number one is I can use optimization problems. And the second thing it's really good at is a pattern completion. And I'll talk just a little bit about each one, and then we'll probably call it good. All right, so a classical optimization problem that people have used these recurrent networks to solve, and when they're used like this, sometimes they're called Hopfield nets. After J.J. Hopfield, which was featured in one of those magazine articles from a long time ago that I gave you right at the beginning of the semester. He's like a founder of how to build and do neural nets. And he did some of these. So the idea here is that I have a bunch of cities, meaning like Hutchinson, Wichita, Kansas City, Chicago, right? So I just have a whole bunch of cities geographically laid out on a map. It's called the traveling salesman problem, but maybe we should call it the Amazon distribution problem. Although they have a bunch of trucks. Anyway, so the idea here is you have one salesman that starts out in this city, and he needs to visit each city once. And only once. And you want him to be able to do that in a minimum amount of time. So that's the optimization. You want to optimize the length or the time that he's going to spend traveling to all these cities to visit customers.
I think I saw something similar to this where they had bees and they tracked the bee location. They set up like a bunch of different areas they needed the bees to visit. And over time, the bees started to approach a circle in the way they traveled rather than just going out in different places. So like they set up a whole bunch of different locations. They knew the most mathematically efficient way to do it. And the bees eventually approached the most efficient way to do it.
Right, and you wonder how they figured that out. Maybe it's because the bees that don't do that die, right? Or they get less honey, and so they get less nourishment, and then, you know, maybe it's like a genetic algorithm. Yeah, so there's all kinds of, and you go, well, this is a city problem, but there's all kinds of optimization problems that occur in manufacturing, in industry, in delivery routes, routing of aircraft. The world is filled with these kind of optimization problems. And it turns out that the classical methods for doing optimization for this work really well up to about 6 or 7 cities, but then once you get past that, it expands non-polynomial. In other words, it just exponentially, the time it takes to calculate the solution goes way up. And Hopfield and some other people came along with neural nets and said, we can solve this in just normal time, just linear time. So you add another city, it just takes a little bit longer. So you can go up to 100 cities and still solve it with the neural net in parallel, and it would take a computer 100,000 years to do it. So the Hopfield net with the recurrence is set up with the paths between the cities as the weights, and then a cost function of the time it takes to do all that visiting. And what the recurrent net does is it runs forward in time and finds the minimum of the cost function that solves this problem. So really, it's a minimization process. That if you set the weights up correctly with the distances between the cities, this thing converges to tell you which order to go to the cities in that the salesman should go. You get beyond that, it would take like 2 weeks, and the intent of this class is not optimization. But I just want you to be aware that if you hear about Hopfield nets, it's different than the feed-forward nets we're talking about in here. It's probably an optimization problem that they're solving. The big interesting thing, people use this for a while and then kind of quit doing it because other methods came out. But then a company called D-Wave, ever heard of them? They're based in Vancouver, Canada. They built a quantum computer that used these kind of optimization problems or optimization methods with quantum computer bits to solve optimization problems in parallel, because the way the quantum mechanics works is each little electron or quantum device does its own thing, but it's connected to everybody else in the system. And the potential for quantum computing is that you can solve problems that you can't even solve with classical computers. We'll see what happens. So D-Wave implemented something like these. D-Wave. You want to look them up, I think it's just do a search on D-Wave. Actually, I think the website is D-Wave System.com. And so they're solving optimization problems using quantum mechanics and something like a Hopfield neural net. All right, so that's one use of recurrent nets. And again, I want you to become just familiar with the term so that if somebody's talking about it or you hear about it, you know what it's doing. Yeah.
So you mentioned the weights as the distance between cities. So then do you need a weight for like X to every single city for each city?
Yeah, you have to set up the structure so that this geometry of the problem is encoded in the Hopfield net. And then it calculates the answer. So the big difference, what we do is we feed data to it and we train the weights, right? Whereas with this kind of problem, the weights are determined by the problem, and as it runs, it finds the solution to the problem. So there is no training or learning in this. And like I said, to get into it in more detail, to actually, for you to go, oh yeah, I see how that works, it would take a little bit of time. But if you want to, do a Google search on traveling salesman problem solved with Hopfield nets, and you can read about it. Okay, let's see, the other thing is pattern completion. So also in these recurrent networks, you can store patterns, and they're stored as weights, just like the cities are stored in weights. So you can store patterns in the weights. So imagine a grid that are pixels and letters. And we'll talk later on a different way to solve this problem. But you could store like the letter A like this. It's going to be a little hard to read, but it's an A, right? You see an A there? Maybe if you don't take your glasses off. So you can store letters as activations in a network. There's a mechanism, again, we don't have time to go through the theory. There's a mechanism to take a whole bunch of different patterns and figure out weights that store those patterns so that the network will recall the pattern with this recurrence thing. So you figure out the weights from a set of patterns, and then if you start the initial state of the recurrent net near one of those patterns, it will actually converge to the pattern that you stored in it. So you store, say, all the letters of the alphabet, and then you can feed those initial conditions a pattern that's missing part of it. And if it's close enough to one of those stored patterns, the Hopfield net or the recurrent net will actually converge and fill back in and complete the pattern. So that's pattern completion. So it can, essentially, it will kind of denoise data. It matches noisy data that's missing and incomplete with what it already knows, and so it fills in the information. In fact, your brain does this, right? You have the ability to recognize a chair even if part of it's blocked off, right? So your brain is doing kind of a pattern completion or pattern recognition. So those are the two main ways that the recurrent networks are used. And again, we won't do much more with this in this class because these are kind of outside the scope of what we do for controls. Although you could see that maybe we could represent a dynamical system as a recurrent net, right? Where the time evolution of these system models could be represented as a recurrent network. But we're not going to go that far with it as far as this class. All right, so I thought that was a good aside. You're not responsible for this for the test. I just wanted you to be aware that these kind of networks are out there as well. And some people use them for different things. Okay, that's it for today. Go home, study for the test, work on your project, or get your vaccine. Essentially.
So it's a homework based project still do a Monday, right?
Yeah.